January 19th, 1945. Somewhere east of Bastogne, Belgium. The captured M18 Hellcat sat in a forward assembly area behind German lines, its white American star hastily covered with Wehrmacht grey paint and a Balkenkreuz stenciled on the turret. Hauptmann Klaus Becker of the 2nd Panzer Division circled the vehicle slowly, his boots crunching through ice-crusted snow, his engineering notebook already open to a fresh page. This wasn't the first American tank destroyer his unit had captured during the Ardennes offensive, but it was the first one taken completely intact, with a full combat load of ammunition, a working engine, and, most remarkably, after 3 weeks of brutal winter warfare, not a single mechanical failure logged in its maintenance records. The mathematical assumptions that had guided German armoured vehicle design for 5 years were about to collide with 18 tons of American automotive engineering that prioritised principles German designers had systematically ignored. Speed over protection, reliability over theoretical performance, operational availability over impressive specifications. The Hellcat represented everything German doctrine said couldn't work in armoured warfare. And yet, examining the odometer reading and the pristine condition of its drivetrain, Becker could already see the uncomfortable truth. It worked extraordinarily well. The vehicle bore tactical markings from the 705th Tank Destroyer Battalion, Company B, serial number USA 1940-327, built by Buick Motor Division in Flint, Michigan, and belonging to a unit that had been hammering German armour positions since the initial breakout from Normandy 7 months earlier. German intelligence had compiled fragmentary reports about American tank destroyers, fast vehicles with open turrets that hit from ambush and vanished before counterfire arrived. But intelligence reports couldn't convey the physical reality of the machine, how light it felt compared to German vehicles of similar armament, how simple its systems appeared upon inspection, how everything about its design suggested priorities fundamentally different from what German engineers had pursued. Becker ordered the Hellcat towed 15 kilometers back to the division's maintenance company at WWII, where mechanics and technical specialists could conduct a comprehensive examination. The Army High Command had issued standing orders that all captured American armoured vehicles in operational condition must be thoroughly documented before being pressed into German service. The Eastern Front was consuming tanks faster than factories could replace them. Understanding American production methods and design philosophy had become as important as capturing territory. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. As the recovery vehicle pulled the M18 through frozen Belgian roads, German tankers from nearby Panther and Panzer IV units gathered to watch. They'd been fighting American armour for months, trading shots with Shermans and dodging tank destroyer ambushes. But seeing an enemy vehicle up close, intact and operational, made the reports real in ways battlefield glimpses never could. The Hellcat looked impossibly fragile, armour that seemed thin enough to punch through with a hammer, an open top that left the crew exposed to everything from small arms fire to artillery fragments. And yet American crews drove these machines into combat daily, racked up kill counts that exceeded anything German propaganda would admit, and survived encounters with Panthers and Tigers that should have slaughtered them. The contradiction demanded explanation. German tank doctrine, refined through years of Eastern Front combat and technical development stretching back to 1938, emphasized 3 principles above all others: firepower sufficient to destroy enemy armour at maximum range, armour protection adequate to survive return fire during engagement, mechanical sophistication that maximized theoretical performance characteristics. These principles had produced the Panther, with its powerful 75mm gun and sloped frontal armour that could deflect most Allied tank rounds. They'd produced the Tiger, a mobile fortress that dominated any battlefield it could actually reach. They'd produced a generation of armoured vehicles that looked fearsome on paper, possessed specifications that impressed engineering review boards, and broke down with soul-crushing regularity under field conditions. The Americans had apparently ignored all 3 German principles and designed something that shouldn't work, according to conventional armoured warfare theory. Yet Becker's preliminary inspection already revealed troubling evidence. The Hellcat's drivetrain showed minimal wear despite documented combat operations spanning 7 months. Its engine, a Continental R-975 radial aircraft engine adapted for ground use, appeared to require almost no specialized maintenance. Its automatic transmission, the Torqmatic system that eliminated the need for manual gear shifting, seemed nearly foolproof in operation. Everything about the vehicle suggested American engineers had asked different questions than their German counterparts. Not, how much armor can we add, but how little armor do we need? Not, what's the maximum theoretical performance, but what will actually work under field conditions with ordinary crews? Not, how sophisticated can we make this, but how simple can we make this and still achieve mission objectives? Late January 1945. Division Maintenance Company, Houffalize, Belgium. The Hellcat arrived at the maintenance facility mounted on a tank transporter, drawing immediate attention from every mechanic and technical specialist in the compound. Chief Warrant Officer Ernst Mueller, the division's senior automotive engineer with 15 years' experience in armored vehicle development, began the systematic inspection that would occupy his team for the next 3 days. German technical intelligence had established rigorous protocols for examining captured equipment, photograph every component from multiple angles, measure every dimension with precision instruments, document every design feature that differed from German practice, disassemble key systems to understand construction techniques and manufacturing methods, test the vehicle under controlled conditions to evaluate performance characteristics. The goal wasn't just understanding what the Americans had built, but why they'd built it that way, and what that revealed about their industrial capabilities and tactical doctrine. Mueller started with the hull structure, immediately noting construction techniques that seemed almost crude by German precision engineering standards. The Hellcat used welded rolled steel plates rather than cast armor sections. Welding required less sophisticated manufacturing equipment than casting, could be performed by workers with basic metalworking training, and allowed rapid assembly using components from multiple suppliers. German vehicles increasingly relied on cast armor that required specialized foundries, took weeks to produce, and created supply bottlenecks that limited production rates. The American approach sacrificed some theoretical strength for massive gains in manufacturing speed and flexibility. The armor thickness measurements shocked everyone examining the vehicle. Maximum frontal protection measured 1 inch. The sides were 3/4 of an inch. The rear plate was 1/2 inch. By comparison, German Panther tanks carried 3.5 inches of frontal armor, sloped at 55 degrees for maximum effectiveness. Even the Panzer IV, Germany's medium tank workhorse, had 3 inches of frontal protection on late model variants. The Hellcats' protection seemed suicidal by German standards. Any German tank gun from 37mm up could penetrate this armor at combat ranges. Any dedicated anti-tank weapon would punch through effortlessly. Artillery fragments that would bounce off a Panther would shred the Hellcat's hull. Mueller documented these measurements with growing confusion. How did American crews survive in vehicles this vulnerable? The answer began emerging as he examined the powertrain. The Continental R-975 engine sat in the rear hull, accessible through large hatches that mechanics could open without specialized tools. This radial aircraft engine, originally designed for training planes, delivered 400 horsepower from a 9-cylinder layout that weighed roughly 800 pounds. German tank engines of comparable power output weighed twice that, required complex cooling systems, and demanded constant maintenance by skilled technicians. The R-975 was air-cooled, eliminating the vulnerable coolant systems that plagued German vehicles. It used a simple magneto-ignition system that worked reliably under conditions that would disable German electrical systems. And most remarkably, the engine showed almost no wear despite the vehicle's documented 7 months of frontline service. Mueller had personally witnessed Maybach engines in Panthers, requiring complete rebuilds after less than 1,000 kilometers of operation. This American aircraft engine adapted for ground use appeared capable of many times that endurance. The transmission examination revealed even more troubling disparities. The Torqmatic automatic transmission used a hydraulic torque converter and planetary gear sets that shifted automatically based on vehicle speed and load. German tankers spent weeks learning complex double-clutching techniques and precise throttle management to avoid damaging their manual transmissions. American crews apparently needed minimal training because the transmission did the thinking for them. This wasn't theoretical sophistication for its own sake. This was practical engineering that reduced training time, prevented operator error, and kept vehicles operational under conditions where German equipment failed. The final drive inspection completed Mueller's growing unease. The Hellcat used helical cut gears in robust housings that showed no signs of stress or pending failure. German Panthers employed final drive systems inherited from Tiger development, a configuration that used straight-cut gears in inadequate housings. These final drives failed catastrophically under combat stress, sometimes after less than 100 kilometers of operation. German mechanics across every front had reported Panthers abandoned due to final drive destruction, vehicles with working engines and intact guns rendered immobile by drivetrain components that couldn't handle the loads imposed by 45-ton vehicles. The Hellcat, at 18 tons with comparable power transmission requirements, used components that appeared overbuilt by German calculation standards. American engineers had built-in design margins that seemed wasteful until you considered field reliability. Extra strength meant components lasted through conditions that would destroy precisely calculated German parts. Testing began on January 23rd under cold, overcast conditions that matched the miserable weather that had characterized the entire Ardennes campaign. Mueller assigned his best test driver, Feldwebel Otto Richter, to operate the Hellcat through a series of trials designed to stress every system. Richter had driven every German armoured vehicle type and numerous captured Allied tanks. His experience would provide valuable comparative insights. The first test was simple acceleration from a standing start. Richter engaged the transmission, pressed the throttle, and the Hellcat launched forward with force that slammed him back against his seat, 0 to 30 miles per hour in, under 12 seconds on packed snow. German vehicles of comparable weight needed twice that time under good conditions. The sustained acceleration continued smoothly through higher speeds until the vehicle reached 45 miles per hour on the straight test road, limited more by terrain conditions than engine power. On paved roads, intelligence reports claimed the M18 could exceed 55 miles per hour, making it the fastest tracked combat vehicle in the world. Richter tested the turning radius, executing pivots that would have strained German transmissions. The Torqmatic handled every maneuver without complaint, never requiring double clutching, never demanding careful throttle coordination. An inexperienced driver could operate this vehicle competently after minimal training. German vehicles demanded specialists because their systems punished mistakes. American vehicles appeared designed for ordinary soldiers with basic skills. The cross-country mobility trial revealed the Hellcat's most impressive characteristic: the vehicle's low ground pressure, achieved through relatively light weight distributed across wide tracks, allowed it to traverse soft ground that would bog down heavier German vehicles. The suspension, using torsion bars like German designs, absorbed rough terrain smoothly while maintaining stable gun platform characteristics. Engine power never faltered, despite sustained high-speed operation across varied terrain. The cooling system handled loads that would cause German engines to overheat. Everything worked exactly as designed, with no apparent weaknesses or pending failures. After 2 hours of aggressive driving that would have revealed problems in most vehicles, Richter returned to the maintenance facility and reported his findings to Mueller. Herr Hauptmann, this vehicle handles better than any German tank I've driven. The automatic transmission is superior to our manual systems in every practical measure. The engine never struggled, regardless of load or terrain. If I didn't know this was enemy equipment, I'd request immediate adoption into our service. Mueller nodded grimly. He'd reached similar conclusions through his technical examination. The Americans hadn't built a better tank destroyer through superior theoretical knowledge. They'd built it through decades of civilian automotive industry experience that Germany had never developed at comparable scale. Before the war, American automobile ownership was widespread, with vehicles common among ordinary citizens across all economic classes. American manufacturers had spent 30 years perfecting mass production techniques, reliable powertrains, and simple systems that worked under varied conditions with minimal maintenance. They'd learned through millions of vehicles and billions of operational hours what actually mattered for reliability versus what looked impressive in specifications. Germany had limited civilian automotive industry by comparison. Cars remained luxury items for the wealthy and party elite. The Volkswagen program, promised to German workers since 1934, had delivered fewer than 1,000 civilian vehicles by 1939. German automotive engineering emphasized precision and theoretical optimization, but lacked the brutal practical experience that American mass production provided. This disparity appeared clearly in the Hellcats' design. Every system prioritized field reliability over maximum theoretical performance. American engineers accepted good enough rather than insisting on perfect, understanding that good enough equipment that actually worked beat perfect specifications that broke down constantly. February 2, 1945 brought new examination subjects. 2 additional M18 Hellcats reached the division after being captured near Streetvith during the final German withdrawals from the Ardennes. Both vehicles were damaged, one with track damage from a mine strike, the other with a destroyed transmission from a direct hit that had killed 2 crew members, but left the hull otherwise intact. Mueller's team could now conduct comparative analysis across multiple vehicles and examine internal components that required disassembly. The track examination revealed another American advantage. M18 tracks used rubber-bushed steel pins that absorbed shock and reduced mechanical noise. German tracks employed metal-on-metal designs that required constant maintenance, wore rapidly, and created distinctive clanking sounds that announced German vehicle positions from hundreds of meters away. The American rubber bushings lasted longer, ran quieter, and required replacement less frequently. Small details like this, multiplied across dozens of components, explained why American vehicles maintained higher operational availability than German equivalents. The transmission disassembly from the destroyed vehicle provided unprecedented insight into American manufacturing philosophy. Every gear, bearing, and shaft showed evidence of mass production techniques that German industry had never mastered for military applications. Components had generous tolerances that would horrify German precision engineers, yet everything fit together correctly and functioned reliably. Parts were clearly designed for easy replacement, with fasteners and connections that required only basic tools. German transmissions demanded specialized equipment and factory-level expertise for many repairs. The destroyed crew compartment told its own grim story about the Hellcats' vulnerability. The penetrating hit had torn through the thin side armor effortlessly, killed instantly with massive trauma, and destroyed internal equipment across a wide radius. An equivalent hit on a Panther might have wounded crew members without catastrophic damage. The open turret meant there was no protection from above against artillery airbursts or attack aircraft. Every German criticism about the M18's lack of protection was entirely valid. American crews who operated these vehicles faced death from weapons that wouldn't threaten German tankers in heavier vehicles. Yet Mueller understood the grim calculus that made this vulnerability acceptable. The Hellcat wasn't designed to trade shots with enemy armor. Its entire tactical doctrine, evident from examining the vehicle and reading captured American field manuals found in the wreckage, emphasized avoiding direct combat through speed and positioning. See the enemy first. Engage from ambush at favorable angles. Destroy the target with a single well-placed shot. Reposition immediately before return fire could arrive. Never fight on the enemy's terms. Never give them a clean shot at you. This doctrine required vehicles fast enough to control engagement range and timing. It required reliable powertrains that wouldn't break down during rapid repositioning. It required simple systems that ordinary crews could operate under extreme stress without making fatal errors. The Hellcat provided all of these characteristics by accepting vulnerability that German designers would never tolerate. The Americans had apparently decided that mobility was better armor than steel plate, at least for specialized tank destroyer units whose mission was hunting enemy armor rather than holding territory. The philosophical difference crystallized as Mueller compiled his technical report for higher headquarters. German armored vehicle design emphasized surviving hits through thick armor and powerful defensive capabilities. American tank destroyer design emphasized not getting hit through superior mobility and tactical positioning. Both approaches could work if executed properly, but the American approach required far less industrial sophistication, used dramatically less strategic materials like armor plate, and could be manufactured much more quickly than German heavy armor. Mid-February 1945 brought orders from Army High Command. All 3 captured M18s were to be moved to the testing facility at Kummersdorf, south of Berlin, for comprehensive evaluation by specialists from the Army Weapons Office. The vehicles would join a growing collection of captured Allied equipment that German engineers were studying with increasing desperation, looking for lessons that might somehow reverse the Reich's deteriorating military situation. The journey north took 5 days, with the operational Hellcat driven under its own power while the damaged vehicles travelled on rail transport. German crews, who operated the intact M18 during this movement, reported the same observations Mueller's team had documented. Exceptional reliability, easy operation, impressive cross-country performance, and terrifying vulnerability to any weapon capable of penetrating its minimal armor. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The Hellcat arrived at Kummersdorf on February 18, 1945, entering a facility that had been examining captured enemy equipment since the war's beginning. Here, in the proving grounds where German armor had been tested and refined for years, American design philosophy would be analyzed by engineers who had created the Panther and Tiger. The examination would confirm what frontline troops already knew. The Americans had built exactly what their doctrine required, prioritizing different values than German engineering culture accepted, and achieving operational effectiveness through means German designers had systematically dismissed as inadequate. Kummersdorf Proving Ground had examined dozens of captured Allied vehicles since 1940, accumulating technical intelligence that revealed uncomfortable truths about comparative industrial capabilities. Soviet T-34 tanks demonstrated sloped armor principles that influenced Panther development. British Churchill tanks showed excellent cross-country mobility despite their archaic appearance. American Sherman tanks proved that automotive reliability mattered more than specifications suggested. Now the M18 Hellcat would add another data point to Germany's growing understanding of how far behind their industrial base had fallen. Ober-Ingenieur Friedrich Hauptmann led the Kummersdorf examination team, bringing 20 years of armoured vehicle development experience to the analysis. He'd worked on early panzer designs in the 1930s, contributed to Tiger development, and consulted on Panther improvements after the catastrophic reliability problems that plagued early production. Hauptmann understood German armor philosophy intimately because he'd helped create it. Examining the Hellcat would force him to confront how much of that philosophy was built on flawed assumptions. The initial inspection began February 19th in a heated examination hall that protected both the vehicle and the inspection team from brutal winter weather. Hauptmann's specialists documented every measurement, photographed every component, and recorded observations that would fill hundreds of pages of technical reports. The methodical German approach to technical intelligence left nothing undocumented, even when the findings contradicted preferred narratives about German technical superiority. The weight distribution analysis revealed the first major insight. The Hellcat's 18-ton combat weight included a full fuel load, 76mm gun with 55 rounds of ammunition, 5 crew members, and all operational equipment. By comparison, German vehicles of similar armament weighed substantially more. The Panzer IV, with a comparable 75mm gun, weighed 25 tons. The Jagdpanzer 38 Hetzer tank destroyer, mounting a similar gun in a lighter chassis, still weighed 16 tons with far less mobility. American engineers had somehow built a vehicle with superior speed and comparable firepower while using less material than German designs required. The explanation lay in systematic weight reduction across every component. The hull used welded rolled steel in the minimum thicknesses acceptable for structural integrity, not the maximum thicknesses desired for protection. The turret was open-topped, eliminating roughly 3 tons of steel that would be needed for a fully enclosed design. The engine was an adapted aircraft radial weighing 800 pounds versus German tank engines exceeding 1,600 pounds. The transmission used lightweight aluminum housings that would seem inadequate by German standards but proved perfectly adequate in practice. Hundreds of small decisions, each prioritizing weight reduction, accumulated into a vehicle that achieved its mission with minimal mass. German designers, working within a military culture that valued protection and emphasized survivability, would never make those choices. Hauptmann noted in his preliminary report that the American willingness to accept vulnerability in exchange for mobility represented a fundamental philosophical difference that extended beyond engineering into tactical doctrine and institutional culture. German officers expected their vehicles to protect crews during direct combat. American tank destroyer doctrine expected crews to avoid direct combat through superior positioning and rapid displacement. Both approaches were rational within their respective operational concepts, but the American approach required far less industrial investment per vehicle produced. The powertrain examination consumed 3 full days of intensive analysis. Hauptmann's engine specialists disassembled the Continental R-975 completely, measuring tolerances, examining wear patterns, and documenting construction techniques. What they found challenged everything German precision engineering valued. Manufacturing tolerances were loose by German standards, with clearances that would trigger quality control rejections in German factories. Surface finishes on internal components showed machining marks that indicated rapid production without extensive hand-fitting. Bearings and bushings used materials adequate for purpose rather than optimal for maximum theoretical performance. Yet every component showed minimal wear despite documented operational service spanning 7 months and an estimated 1,500 kilometers of combat operations. The loose tolerances apparently didn't matter, because American metallurgy and lubrication systems compensated for manufacturing imprecision. The adequate materials proved entirely sufficient for the actual loads and stresses the engine encountered in field service. The rapid production techniques delivered an engine that worked reliably, rather than one that met theoretical perfection standards that broke down under practical conditions. German engine development had pursued exactly the opposite path. Maybach engines in Panthers used precision-machined components with tight tolerances, exotic materials selected for maximum strength-to-weight ratios, and complex systems that extracted every possible unit of power from each kilogram of engine mass. The result was engines that produced impressive power outputs on test stands, looked sophisticated in technical specifications, and required constant expert maintenance under field conditions, while frequently failing after relatively short operational periods. The American R-975 produced less power per unit weight than German engines, used simpler technology, and required minimal specialized maintenance, but it worked consistently, tolerated abuse from inexperienced crews, and kept running under conditions that disabled German power plants. Hauptmann understood immediately that this represented maturity in automotive engineering that Germany fundamentally lacked. American manufacturers had refined these principles through decades of civilian vehicle production, learning through millions of engines what actually mattered for reliability versus what merely looked impressive on paper. The transmission analysis reinforced these conclusions. The Torqmatic automatic system used hydraulic controls and planetary gear sets that shifted based on vehicle speed and throttle position without driver intervention. German engineers had experimented with hydraulic transmissions for the Ferdinand tank destroyer, creating a complex electric drive system that provided excellent theoretical performance and catastrophic practical reliability. The Ferdinand's transmission problems were legendary among German tankers, with vehicles frequently disabled by electrical failures or hydraulic leaks that left them immobilized. The Hellcats Torqmatic appeared less sophisticated in some respects, using simpler control logic and more robust components. But it worked. Test drivers at Kummersdorf reported that after minimal familiarization, they could operate the M18 as easily as driving a civilian truck. Acceleration was smooth. Shifts occurred automatically at appropriate points. The system tolerated aggressive driving that would destroy German manual transmissions. Once again, American engineers had prioritized practical functionality over theoretical optimization, and the results spoke clearly in favor of their approach. March 7, 1945, brought expanded testing as additional captured M18s reached Kummersdorf from various sectors of the collapsing Western Front. The proving ground now possessed 5 Hellcats in various conditions, allowing comparative analysis and long-term reliability testing. Hauptmann organized an evaluation program that would have been comprehensive if time and fuel supplies had been unlimited. With Soviet forces advancing from the east and Germany's strategic situation deteriorating daily, the testing proceeded with desperate urgency. The mobility trials demonstrated capabilities that shocked even experienced test drivers. The Hellcat accelerated from 0 to 50 km per hour in under 10 seconds on paved surfaces. Maximum speed exceeded 85 km per hour, limited more by track design than engine power. Cross-country performance through rough terrain matched or exceeded any German vehicle, with the low ground pressure allowing the M18 to traverse soft ground that bogged down heavier Panthers. The suspension handled high-speed movement smoothly, maintaining gun stability that would be critical for engaging targets during rapid displacement. German test drivers compared the Hellcat directly against Panther and Jagdpanzer 38 vehicles in head-to-head trials. The Panther, with its powerful 700 horsepower Maybach engine, could match the M18's acceleration, but not its top speed. The Panther's 45-ton weight versus the Hellcat's 18 tons meant the German vehicle couldn't achieve comparable mobility, despite superior power-to-weight ratio on paper. Real-world performance depended on transmission efficiency, track design, and suspension characteristics, all areas where the American vehicle demonstrated advantages. The Jagdpanzer 38T, Germany's light tank destroyer built on Czech chassis, was mechanically reliable by German standards but dramatically slower than the Hellcat. Maximum road speed barely exceeded 40 km per hour, less than half what the M18 achieved. In tactical terms, this meant American tank destroyers could reach threatened sectors twice as fast as German equivalents, control engagement, timing through superior mobility, and disengage before German vehicles could pursue effectively. Hartmann's interim report to the Army Weapons Office, dated March 15, 1945, contained observations that would never appear in official propaganda, but couldn't be hidden from technical specialists. The American M18 Hellcat represented armored vehicle design optimized for mass production and tactical doctrine that emphasized mobility over protection. German vehicles represented design optimized for individual combat superiority and specifications that looked impressive but proved difficult to maintain under field conditions. In purely technical terms, the American approach was superior for modern industrialized warfare, where operational availability and production numbers mattered more than individual vehicle capabilities. The report noted that Germany lacked the industrial capacity to replicate American design philosophy, even if German doctrine accepted the vulnerability that philosophy required. Building vehicles as light as the Hellcat required confidence in mass production capability that could replace losses quickly. Germany couldn't replace vehicles quickly regardless of design, making survivability through armor protection essential for German tactical doctrine. The circular logic was inescapable. German vehicles needed heavy armor because German industry couldn't produce enough vehicles to accept higher loss rates, but heavy armor created reliability problems that reduced operational availability and negated numerical advantages. American industry produced vehicles fast enough that accepting higher vulnerability was strategically rational. Light armor meant faster production, and faster production meant more vehicles reached the front. More vehicles meant numerical advantages that compensated for individual vulnerability. The mathematics favored the American approach, but only if you possessed American industrial capacity. Germany didn't and never would. Field reports from German units using captured M18s reinforced Kummersdorf findings with practical combat experience. The 2nd Panzer Division operated their captured Hellcat in reconnaissance and mobile reserve roles through February and into early March, accumulating dozens of operational hours under actual combat conditions. Unit after-action reports praised the vehicle's mobility and reliability while noting vulnerability concerns that proved less critical than expected because proper tactics minimized exposure to enemy fire. German crews learned to employ the Hellcat exactly as American doctrine specified, position in concealment with clear firing lanes and multiple withdrawal routes planned in advance. Engage targets from ambush at ranges and angles that maximized penetration probability. Fire and immediately displace before enemy forces could locate and target the firing position. The tactics worked when executed properly, allowing the thinly armored vehicle to survive encounters that would seem suicidal in conventional direct combat. Several German tank destroyer crews who transferred from Jagdpanzer units to captured M18s reported in letters and informal communications that they preferred the American vehicle despite its vulnerabilities. The reliability meant they could execute missions without constant worry about mechanical failures, stranding them in exposed positions. The speed meant they controlled engagement timing rather than being forced into disadvantageous combat by slow vehicles that couldn't reach positions quickly enough. The automatic transmission meant they could focus on tactical considerations rather than complex driving techniques that demanded constant attention. These preferences never appeared in official reports because admitting that enemy equipment was superior to German designs contradicted the propaganda narrative about German technical supremacy. But technical intelligence analysts collected and documented these observations, understanding that honest assessment of enemy capabilities was essential for effective countermeasures, even when those assessments were politically uncomfortable. April 3, 1945, brought the final comprehensive test program before Soviet advances forced Kummersdorf's evacuation. Hauptmann's team conducted endurance trials, pushing the operational M18s through hundreds of kilometers of sustained, high-speed movement, measuring fuel consumption, monitoring mechanical systems, and documenting any failures or degradation in performance. The results provided definitive data on American automotive engineering superiority. The Hellcats maintained operational availability exceeding 90% throughout the testing period, requiring only routine maintenance that mechanics with basic training could perform using standard tools. Fuel consumption averaged roughly 140 litres per 100 kilometres under mixed driving conditions, comparable to German vehicles despite the M18's superior performance characteristics. The engines showed no signs of pending failure even after sustained high-load operation. Transmissions required no adjustment or repair. Final drives, the component that plagued German vehicles with catastrophic failure rates, performed flawlessly throughout testing. By comparison, Panther tanks at Kummersdorf required constant maintenance intervention to maintain operational status. Final drive problems remained endemic despite design improvements implemented since 1943. Transmissions demanded careful operation and frequent repair. Engines needed regular valve adjustments, carburetor tuning, and specialized attention from trained mechanics. Operational availability averaged below 50%, even under ideal proving ground conditions with unlimited spare parts and expert maintenance personnel. Field units reported availability rates sometimes dropping below 25% when spare parts were scarce and combat conditions prevented proper maintenance. The disparity was undeniable and damning. American vehicles worked reliably with minimal maintenance. German vehicles broke constantly despite maximum effort from skilled mechanics. The difference wasn't German incompetence or American genius. It was decades of automotive industry maturity applied to military production versus precision engineering culture that valued theoretical sophistication over practical reliability. Hauptmann drafted his final report to Army High Command on April 18, 1945. Knowing the document would likely never receive serious consideration given Germany's collapse. Soviet forces were within artillery range of Berlin. American and British armies had crossed the Rhine and were advancing against crumbling resistance. The Third Reich had perhaps weeks remaining before total defeat. Technical intelligence about enemy tank destroyers seemed irrelevant when the entire military structure was disintegrating. Yet Hauptmann wrote the report anyway, compiling his findings with the same methodical precision that had characterized his entire career. Future historians and engineers might learn from these observations, even if current leadership couldn't act on them. The lessons were clear enough. Industrial capacity mattered more than individual weapons specifications. Reliability determined operational effectiveness more than theoretical performance. Mass production of adequate equipment beat limited production of sophisticated equipment that broke down constantly. American automotive engineering maturity gave them decisive advantages that German precision engineering couldn't overcome. The report concluded with observations that summarized everything Kummersdorf testing had revealed. The M18 Hellcat represented American industrial philosophy applied to armored warfare. Lightweight for rapid production, simple systems for easy maintenance, reliable components for high operational availability, adequate protection for mission requirements rather than maximum protection regardless of cost. The vehicle succeeded brilliantly at what it was designed to accomplish. German vehicles, designed according to different principles emphasizing protection and sophistication, succeeded less consistently because those principles required industrial capabilities Germany didn't possess. April 21, 1945 brought evacuation orders as Soviet artillery began ranging on Kummersdorf. Engineers frantically packed technical documents and shipped them west, hoping to preserve intelligence data for whatever German military force might exist after the inevitable defeat. The captured vehicles, including the M18 Hellcats, were pressed into service with improvised combat units defending the approaches to Berlin. German crews who had tested these vehicles now operated them in desperate defensive battles against the Soviet armies that had destroyed German armor across the Eastern Front for 4 years. The irony wasn't lost on anyone involved. Vehicles designed and built by Americans, captured during Germany's last failed offensive in the West, now fought in Germany's final defensive battles in the East. The Hellcats performed as reliably in combat as they had during testing, continuing to function when German vehicles around them broke down from mechanical failures or lack of fuel and spare parts. One M18, operated by a scratch crew from Kummersdorf's test driver pool, engaged Soviet T-34 tanks on the outskirts of Berlin in late April. The vehicle's 76mm gun proved entirely adequate for penetrating T-34 armor at combat ranges. The crew executed proper shoot-and-scoot tactics, firing from concealment and displacing before Soviet return fire could locate them. They claimed 3 confirmed kills before running out of ammunition and abandoning the vehicle when Soviet infantry threatened to overrun their position. The Hellcat was still mechanically functional when the crew left it. The engine ran smoothly, the transmission shifted properly, the tracks and running gear showed no signs of failure. American automotive engineering remained reliable literally until the final days of the European War, providing tangible proof of industrial superiority that German engineers had documented but German leadership had failed to overcome. May 2, 1945 brought Germany's unconditional surrender. The Thousand-Year Reich ended after 12 years, brought down by military defeat, industrial exhaustion, and the accumulated consequences of strategic decisions that prioritized ideology over practical effectiveness. Among the countless factors that contributed to Germany's collapse, armored vehicle reliability seemed almost trivial, but to the tank crews who fought in vehicles that broke down constantly, to the mechanics who struggled to keep Panthers operational with inadequate spare parts and insufficient time, to the engineers who understood Germany had lost the industrial war years before losing the shooting war, reliability mattered enormously. The M18 Hellcat served American forces through the war's end and into occupation duty, maintaining the operational availability that had characterized its entire service life. Tank destroyer battalions were gradually disbanded as the army reorganized for peacetime, and the specialized anti-tank mission seemed less critical in a world where America's only potential opponent, the Soviet Union, was technically an ally. Most Hellcats went to scrapyards or were transferred to Allied nations under military assistance programs. A handful survived as museum exhibits or private collection pieces, physical reminders of design philosophy that prioritized mobility and reliability over protection and sophistication. The technical intelligence documents compiled at Kummersdorf and other testing facilities survived Germany's collapse, captured by American and British forces advancing through German territory. These files provided Allied intelligence with detailed information about how German engineers assessed American equipment, revealing both the thoroughness of German technical analysis and their ultimate inability to replicate what American industry produced routinely. Post-war examination of these documents by American military historians revealed patterns that German engineers had documented, but German leadership had failed to address. American vehicles consistently outperformed German equivalents in reliability metrics. American automotive engineering reflected decades of civilian industry experience that military applications leveraged effectively. American mass production capability exceeded anything Germany could match even before strategic bombing intensified. German precision engineering culture produced impressive specifications that translated poorly to field reliability under combat conditions. The lessons influenced post-war American armor development, reinforcing doctrinal emphasis on operational availability and maintainability. When the Army developed the M41 Walker Bulldog light tank in the early 1950s, designers consciously prioritized reliability and ease of maintenance over maximum theoretical performance. The vehicle used automotive industry components wherever possible, incorporated generous design margins that prevented overstressing mechanical systems, and featured simplified maintenance procedures that ordinary mechanics could perform without specialized training. The M41 proved highly reliable in service, validating the design philosophy that the M18 Hellcat had exemplified a decade earlier. German post-war armor development, when West Germany was permitted to rebuild military forces in the 1950s, explicitly rejected the protection-obsessed philosophy that had created Panthers and Tigers. The Leopard 1 main battle tank, entering service in 1965, emphasized mobility and firepower over heavy armor protection. Designers intentionally selected lighter armor that provided adequate protection against expected threats rather than maximum protection regardless of weight penalty. The powertrain used reliable components with substantial design margins. Maintenance procedures were simplified to reduce downtime and logistics burden. The Leopard 1 became one of the most successful tank designs of the Cold War era, serving with numerous armies and remaining in production for decades. The direct lineage from M18 design philosophy to Leopard 1 development was clear to anyone who examined both vehicles' engineering priorities. Speed and reliability mattered more than maximum protection. Adequate firepower for mission requirements beat sophisticated weapons that complicated logistics. Simple systems that ordinary crews could maintain beat complex systems that demanded specialists. These principles, proven through combat experience and documented through captured German technical intelligence, became foundational assumptions for modern armor development. The story of German engineers examining captured M18 Hellcats represents more than just technical intelligence and comparative vehicle analysis. It illustrates the fundamental importance of industrial maturity and design philosophy in modern mechanized warfare. German engineers possessed theoretical knowledge equal to or exceeding their American counterparts. They understood automotive principles, metallurgy, and mechanical engineering as well as anyone in the world. But they applied that knowledge according to cultural values that prioritized precision and sophistication over reliability and maintainability. American engineers, trained through decades of mass-market automotive production, understood through hard experience that reliability mattered more than specifications. They knew loose tolerances with good materials beat tight tolerances with inadequate quality control. They recognized that simple systems requiring minimal maintenance beat complex systems that needed constant expert attention. They accepted that adequate protection, allowing higher mobility, was strategically superior to maximum protection that reduced mobility and complicated production. These lessons, learned through millions of civilian vehicles and billions of operational hours, translated directly into military applications with decisive effect. The M18 Hellcat, rolling through frozen Belgian roads under German crews during testing, embodied these principles completely. Every design decision prioritized operational effectiveness over impressive specifications. The vehicle worked reliably because American engineers had built reliability into every component through decades of refinement. It performed its mission successfully because American doctrine matched vehicle capabilities perfectly. and it survived in greater numbers than German equivalents because American industry could produce it rapidly and replace losses quickly. German engineers at Kummersdorf documented all of this methodically, understanding the implications even when their leadership couldn't or wouldn't act on the findings. Their reports, captured and preserved, provide historians with detailed technical assessment from the enemy perspective. Those assessments confirmed what Allied forces knew from experience. American automotive engineering excellence provided decisive advantages that German precision engineering couldn't overcome. The Hellcat wasn't the best tank destroyer because it had the thickest armor. It wasn't the best because it mounted the most powerful gun. It was the best because it worked reliably, reached the battlefield consistently, and executed its mission effectively through superior mobility and tactical employment. When German tankers examined captured M18s and understood why these vehicles hit 55 miles per hour, they weren't just learning about automotive engineering. They were confronting the reality that Germany had lost the industrial war, and all the tactical skill and technical sophistication in the world couldn't compensate for that fundamental defeat. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.